are going. Okay. So we'll start the PowerPoint. So last day that we were in class, actually not the last day, because the last day I told you how to do lab reports. On Monday, we finished off the lesson where I assigned you to draw or use a blank periodic table to label the important groups or and also the important I guess periods. These are periods here, but the important groups on the periodic table, and to make a note of their properties. So to make a note of the properties of the alkali metals, the alkaline earth metals, etc., etc. So hopefully you have completed that. Again, I don't check that stuff. That's for your notes. What I want to talk about today is, again, the periodic table. So you're kind of got a little bit of a head on me. You've made that periodic table. You've got those groups in there. And I want to talk now a little bit more about the periodic table itself. So the periodic table of elements, the organization of elements here. These two pictures here, I just want to explain what they are and what that means. We talked the last day as well in the classification of matter. We talked about the difference between an element and a compound. And I talked about how there were two different definitions for an element and compound. Does anybody remember the two terms that we used? If you could just give me one. What were those terms, those different types of definitions? Does anybody remember what they were called? I'll take one if you've got it. I don't need both. I had this particular type of definition and then the other type. They were in brackets. What were the types of definition? Hannah? Theoretical. And a theoretical definition, remember, is based on an idea. Does anybody remember, and it doesn't have to be the definition, but an element? What is the theoretical idea of what an element is? Does anybody remember that? Yep. Yeah, that's right. It has to do with the atoms. So if it's an element, what's true about the atoms in an element? What's true about the atoms in an element? They're all the same. The atoms are all the same, right? So in an element, the atoms are all the same. What was the name of the other type of definition that we had? It's either theoretical or what was this other one? Any ideas? Yep. It's empirical. Empirical, remember, means that you can sense it, you can see it, you can observe it taking place. Does anybody remember what the empirical definition for an element is? Doesn't have to be word for word. Yep. That's right. We can't break it down chemically. It is the simplest of matter, okay? Now, elements have been known for a long time. They've been known by the empirical definition, right? Prehistoric man, maybe, I don't know. Perhaps, like I said, had a campfire to do something. It was maybe around a certain type of earth that might have contained some copper oxide, and then the carbon and the copper do a chemical reaction. They have no idea what's going on, and in the end, copper is invented, is produced, and like I said, they make weapons out of it, and then they dominate and kill all their neighbors, and they take over the world. Anyway, so elements have been known for a long time. There's a particular scientist that I'm going to make reference to quite a bit, and his name was Antoine Lavoisier. There's my book, Antoine Lavoisier. This is a textbook of mine that I took a course in university on the history of chemical thought. So we talked about ideas in chemistry and where they came from. Now, Antoine Lavoisier did not live that long ago. I'm talking late 1700s, early 1800s, probably about the same time as Dalton. But what Antoine Lavoisier did for chemistry is about the same as what Sir Isaac Newton did for physics, all right? So if you, and Sir Isaac Newton, by the way, he's the other guy on the wall down the hall there. We all know Albert Einstein. We recognize that particular picture. The other guy is Sir Isaac Newton. Now, Sir Isaac Newton, who's taken physics with Mr. Petrus? What is Newton known for? What is Newton known for? Trent, you're obviously a good physics student there. What is Newton known for? Gravity. Somebody's whispering out of gravity. That's good stuff. He's whispering out of gravity. No, that's not even what I'm going for. Nope. No, he's looking. Trent's looking for answers here. It's killing him. By the way, this is all being recorded. Forces. That's exactly what I'm looking for. And not just forces, but he put 3 of these out there. 3 what? Newton's laws. Thank you. See, Trent did know, by the way, for the record. So he put together the 3 laws that governed forces. He put together all the ideas of physics that people had ideas of that came before him, and he put them together in one place and explained lots of stuff. Before Newton, physics was kind of chaotic. People were talking about what happens when objects fall. People were trying to explain what happens when you push something. People were trying to explain why the planets moved the way they did in the sky. And in the end, Newton explained it all with his laws of motion. Chemistry was in the same boat. Chemistry before Lavoisier was chaos. They were reacting various stuff. Everything had a different name depending what part of the world you were in. So if you wanted to talk about something like sulfur, sulfur would have had a certain name in one location, a different name in a different location, and a different name in a third location. So the chemistry that people were doing, they couldn't communicate with each other because they weren't speaking the same words. So what did Lavoisier do? Lavoisier organized chemistry. And one of the main things he did was he made a list of all of the elements. And here I've got a list of the elements according to Lavoisier and his particular book. Now, this is a reproduction of his book. Lavoisier was French. It was originally in French, but this is an English reproduction that was originally printed, again, in the early 1800s. So again, it's a reproduction of the English print. But if we take a look at his list of elements, unfortunately, he got the first 2 wrong. His first one was light. He thought that light was an element itself. We now know it's not. It's a form of energy. But he had to make a list of his stuff, and he thought that was the case. His second one was wrong, too. He puts here heat. They thought heat was made up of an actual substance as well, that in the future somehow someone would be able to measure and weigh the heat. But we now know heat is also a form of energy. So the first 2, not so good. Now, if we move on to the next one, oxygen. Now, that's the name that Lavoisier gave oxygen. Before Lavoisier, and that's the name he gave it. Before Lavoisier, it was called deflagellifikated air. Remember, so it was a description of the way it burnt things. It was crazy. Imperial air. Vital air, because they had discovered that living things couldn't live without this gas. So they called it vital air, vital for life. Base of vital air. The next one he called azote, A-Z-O-T-E. That actually we know now as nitrogen. We didn't call it nitrogen. It was called flagellifikated air as opposed to deflagellifikated air. Mephitis? Oh my goodness. Hydrogen. He gave the name hydrogen. Before that, it was called inflammable air because they knew they could burn it. It would burn quite well. And then sulfur, phosphorus, charcoal. Those names came from not prehistorical, but historical, even before Lavoisier, and he kept those names. So some of the names he got all organized, others already existed. So what did Lavoisier do for elements? He got them all named up and all taken care of so that we could tell what we were talking about. Unfortunately, there was no order. There was no order to the list. It's just probably alphabetical or just the way he wanted to put it down there. So what did Mendeleev, and we're going to talk a little bit about Mendeleev later on. Mendeleev is a scientist that in the mid-1800s put all of the elements in a nice orderly fashion, all right? And so that's what we're talking about today. We're talking about the periodic table and the organization of the elements. So let's talk first just about the table itself and writing down important things about the elements that are found there. And then we will go back and talk again a little bit about some history and about Mendeleev and about how we see the periodic table today. So 88 naturally occurring elements, with the rest being man-made. If you've ever had a chance to look at the periodic table, you'll notice it goes to higher than 88. You'll notice this one goes right on to 118. And I believe that, all of those have been discovered, all right? Historically, discovery would be digging in the ground, find some chemicals, do some chemistry, isolate the element. A discovery of an element. In terms of the ones that are man-made, they had to be created. Now, they're created using things called particle accelerators, right? Right now, the largest particle accelerator that ever has been created by man is up and running. I think it's in under Switzerland and France. Does anybody know what the name of that particular machine is called? Just the letters. I don't need, well, you could give me the whole name. Does anybody know what that's called? Anybody know? It's called the Large Hadron Collider. You may have heard of it in various things. What's that? CERN is kind of like, it's the group that runs the Large Hadron Collider. And so CERN is like a facility or a place. And they have other colliders there as well, but the Large Hadron Collider is the name of the machine that's running now. And it's like not just even a machine, like it's huge. Like it's 30 kilometers in diameter, the ring that runs these particles in it. Anyway, what do? They speed particles up using various magnets and electricity, and they'll take particles like protons and neutrons, and they'll smash them into other elements, and sometimes they'll even take beams of other elements, and they'll try to smash them together, and they hope they can get them to stick together for a very brief amount of time, and then if they can get enough to have 114 protons in it, then they've made 114. It's very unstable. It blows apart and disintegrates, and they look at all the pieces, and then they somehow conclude we've made 114. They don't last very long. Many people say, why do we spend so much money to make these things that only last for microseconds? Well, it's to test the laws of physics, right? We think we know the way the atom is built and the way it works. And if it works the way we believe it does, we should be able to create those. And I believe, at last note, that they have created all the way up to 118 for brief amounts of time. But anyway, that's how we make elements. We'll talk more of that when we talk a little bit about radioactivity next week. All right, two major groups of elements, metals and nonmetals, and that's divided by the classic stair-step line. We've got our metals down to the lower left and our nonmetals up to the right. So metals, I do want you to write this. And again, if you're running a device, you might even have been writing ahead. That's fine. Doesn't matter to me. Yep. Good question. So you don't have to worry about SATP right here at this point in time, but SATP stands for Standard Ambient Temperature and Pressure. It's a standard temperature and pressure that we use to compare properties of elements and compounds. Standard ambient temperature is 25 degrees Celsius. It's a little warmer than room temperature because laboratories tend to have machines running, a Bunsen burner, that type of thing. That warms it up a little bit more than room temperature, so 25. And the pressure is 100 kilopascals. That's very close to what we call regular pressure that you'd experience outside in the weather, right? So it's atmospheric pressure. What that means is, at those conditions, when you look at a periodic table and you see that there's some in gray and red and blue, that means solid, liquid, or solid, gas, and liquid. It's at those conditions we see these particular properties, all right? So in a typical laboratory, all of the metals are solid, with one exception, mercury, all right? So it kind of just means general laboratory conditions, okay? So if you had it in the lab, you'd see it, all these guys being solids, except mercury. They conduct heat and electricity very well because they're metals. They react with oxygen to produce oxides. So things like iron will rust to produce iron oxide. They're malleable and ductile, meaning that you can hammer them flat or you can stretch them into a wire. Malleable means you can hammer it flat. Ductile means you can stretch it into a wire. They have a weak attraction for their outer electrons, so they tend to lose those outer electrons in chemical reactions, all right? So during a chemical reaction, they'll lose those outer electrons to become stable ions. And you can see the majority of the periodic table is metals. Okay, and again, people are either writing from devices or not. If you want me to go back, just let me know, all right? Because there's no way for me to know anymore whether we're ready to roll on or not. So nonmetals, 21 of them are nonmetals. Their atoms are smaller. Their properties are varying. Most of them are brittle, they're dull, and they do not conduct heat or electricity. They have a strong attraction for their outer electrons. And they tend to gain more electrons to get a full outer shell. And as we go through this first part of this first unit, that's really going to be one of our main things we want to talk about. Why is it that the nonmetals gain electrons? Your typical grade 10 answer would be because it wants the full outer shell to be happy. But you're going to learn that atoms don't have little brains, or nor do they have emotions. So there must be another reason that they gain to get that full outer shell. So we want to go from talking about happy atoms to, the real physical reason why they want to gain. There's a way to print that without all that black. I can show you. I've got it figured out. Again, I'm not sure where we're at. People are looking down various things. I'm going to keep rolling here. So a few more now definitions. Oh, actually, no. Before we get to the definitions. Another thing that I test you on is names and symbols for the first 20, along with these. If the quiz was going to be tomorrow, which it's not, I was going to test you on that separately at another time. But now that the quiz has been moved back to Tuesday, I'm going to also put that as part of it. So now our little quiz has grown to safety, periodic table stuff, equipment, and the names and symbols of the first 20, okay? And along with these, because they are important ones. No, you don't have to know the number or position. You just have to know the name and the symbol. The reason I make you do that is because when we start talking about atoms, I need you to be able to quickly scan for those letters to spot the element so that you can find the information on the table. Okay? First 20, we use that all the time, and then these are also very, very common that we use. The way the quiz is going to work is I would give you this little quiz first, no periodic table. You hand me that little part of the quiz on its separate sheet, and then I give you the second part of the safety, periodic table, and equipment quiz, and I also give you a periodic table, because I will let you have a table so that when we're talking about the alkali metals or alkaline earth metals or the transition metals, you have a table to locate the elements on in order to answer the questions. I don't expect you to memorize a periodic table, right? So I would quiz you on this, no periodic table, and then I give you a periodic table. This little quiz here is the only time that you won't have access to a periodic table when doing a test or an evaluation. The periodic table for the chemist is the reference table, is the thing that we need. So that's the only time I will test you without a table. All right? Okay. So now some other important parts of our periodic table. And again, I'm hoping this is predominantly review. I know when I teach the grade 10s, I think I use this note when I teach the grade 10. So it should be very much review. Connor should be completely bored. He says, I've done this before, I think. So the group goes up and down, the vertical, and the period runs across. The group is also known as a family because the characteristics of these elements are very similar. Their properties are similar. Just like in your family, characteristics would be similar. Does that make sense? I guess. Similar hair color, similar, I don't know. I guess that makes sense. The period across the road, properties change from metallic on the left to non-metallic on the right. So in a period, the properties slowly change as you work your way across. The reason it's called a period has to do with its repeating periodic trends. I'll talk about that in a moment when we look at how Mendeleev came up with the periodic table. And again, I have no idea. Can I go on? Can I go ahead? We're good to go? Yes, yes, because again, we've got people using devices, which is okay. And again, this is just a table here. Again, the periods, again, for people who are watching the video, right? So our group goes up and down there, right? That's the group. And the period runs across there. That would be the fourth period. All right? And again, you don't have to write that. That's just for video watchers. Okay. Now, you don't have to draw the map, but I do want to define main group. So main group elements. They include 1 and 2, and then 13 through 17. Actually, put 18. Put 18. I don't want 17. I want 18. Through 18. You can see even here on the picture, I've got 18 included in that. Essentially, we're not including the transition metals and the lanthanides and actinides. Main group elements behave in a very nice, predictable way. They're the elements we predominantly talk about in a course like grade 11 Introduction to Chemistry. We will be talking a little bit about some of the transition metals, but we won't be getting into an explanation on why they behave that way. Their behavior needs another theory on top of what you will be learning. You need to know a little bit about quantum theory in order to explain this. In grade 12, we explain the transition metals and the way they behave. All right? So we will be dealing predominantly with main group elements. Again, we were just writing a couple of lines. So again, let me know if I'm going too fast or too slow. Metalloids, we haven't defined that anywhere. I don't know if that was that on that page 19? Did we define metalloids by doing the groups on page 19? I don't remember. I don't think it was there. That's why I wanted to put it on here. If you've got it twice, then awesome. Got it twice. They're the elements located near the stair-step line. Some have, they have some metallic and non-metallic properties, and aluminum is a little too metallic. They don't include it. Notice it has to be right up against the stair-step line, and therefore something like gallium, right, is not a metalloid. It's not, you know what I mean? It's not right up against it. Gallium is a metal. Okay, at this point, I go through the note, and it has all of those groups and periods that I asked you to write about on page 19, so there's no need to copy this next stuff down. That's what you did if you did the homework where I asked you to label your periodic table. So let's just quickly go through the various important groups and periods. You could get that page out and look along. If you see something that you think might be extra that you might want to add, you could add that to it. But I'm not gonna be waiting around on each slide for you to write this down. Okay? So going through the periodic table and the special groups, the first one we encounter on the left is group 1. It is the alkali metals. They're soft, silver in color. All of them are solids. They react with water violently. All right? So you put the metal in water, it doesn't hang around, it's not like a piece of gold that would just fall into the water. This reacts with the water violently, it produces a basic solution and makes hydrogen gas. And they tend to react with the halogens, that's our group 17 across the way, to make similar compounds to like sodium chloride. They match together perfectly 1-to-1. Does anybody remember why something like sodium gets along so well with something like chlorine? Anybody remember from grade 10 why that's a match made in, I don't know, a test tube? I don't know. Anybody remember why that's the case? Anybody remember what's true about the sodium atom that makes it work so well with the chlorine atom? I'm asking about the electrons. Anybody remember about the electrons? Yeah, at the back there. Yep. Yep, exactly correct. This guy has 1 in its outer ring. This guy needs 1 to fill its outer ring. They do a trade and it's perfect. That's correct. That's the reason. Yep. Okay. Oh, this S here just represents the fact that it's a solid. All right. So group 2, the alkaline earth metals. Again, they're very light and they're reactive. Again, they're solids. They have metallic properties. They tend to react with oxygen to form oxides, and their formula tends to be 1M to 1O, because again, just like the last one, oxygen, remember, needs 2. These group 2 guys have 2. They do a nice trade and they make the oxide. If you are not remembering about the electrons, don't worry. We'll be going over that all over again. I'm just, asking if you can, recall from the last time you took some chemistry. They also react with water as well. Okay, click. Come on, click. Jumping all the way across now at this point. Now you might ask, what about these main group guys in between, 13, 14, 15, 16? They are very, very important elements, with carbon and oxygen and nitrogen probably being the three most important when it comes to living things. But their properties are not distinct. There's, again, that gradual property change as we move over, but the halogens are very distinct. They may be solid, liquids, or gases. You'll notice as we work our way down, we've got all three. They exhibit non-metallic properties. This is a typo. They're not lustrous. So again, for video people, this not needs to go to the front. They're not lustrous. In other words, they're not shiny. And they're not conductors. Again, extremely reactive, fluorine being the most reactive, and they react readily with hydrogen and metals. Okay. Noble gases, they're on group 18, and they're non-reactive. If you recall, they've got that full outer shell. That's why they don't react. Krypton, xenon, and radon, they can be forced to react. We just stated that fluorine was very reactive. If you put fluorine under extreme pressures with these gases, you can get them to make a very unstable compound. Transition metals, so that's in the middle there, 3 to 12. And they have all kinds of varying properties, but they are all metals. Characteristically strong, hard metals with high melting points. Good conductors of electricity. Multivalent, which means they can have more than one charge. Remember, we talked about things like copper 2 and copper 1. We'll go back, we'll be reviewing all that. Many react with oxygen to form oxides. Some will react with solutions of strong acids, all right? These are the metals that we encounter in industrial uses. Things like copper and nickel, right? Zinc is used in batteries. Gold, obviously, jewelry, silver, platinum, palladium. They're strong metals. They don't react like these guys on the left, but they're strong and they're very, they're very functional. They're very useful. Their properties have many practical uses. Lanthanides, down at the bottom. The word lanthanide comes from the fact that lanthanum is the first one in the row, so there's nothing special about it. We have to realize that this number 57 originates after this number 56. So we work our way across period 6, cesium, barium, then we go to lanthanum and work our way across to 71, which then goes back here to hafnium, okay? The table should actually be longer with these two groups at the bottom, the lanthanides and the actinides, being squeezed in. But it doesn't fit nicely on a piece of paper if we do that. So what did they do? They took those two out and put them down at the bottom, okay? So period 6, you run across there, move down to lanthanum. Across period 7, you move from francium, radium, down to actinium, all right? And so the next one is the actinides, elements that have numbers from 89 to 102, and actually even beyond now. That's my old note. No, actually, no, it does go to 102, and then we go beyond there. Okay, that's good. Transuranic. I don't know if this was on that page 19 or not. Transuranic simply means beyond uranium. Uranium is the heaviest naturally occurring element. You can see here on the periodic table, it's filled in with the gray. The silhouettes are man-made, so everything beyond uranium is man-made. All right, and that's the significance of transuranic. They're all man-made. Okay? All right. So here is just a little, and I'll bring the whole thing up. This is just me doing a multiple click here. So here you can see, if you haven't done your periodic table, you haven't taken the image, and if you have, you can check there that you've got all the appropriate things in the appropriate places. Okay? So you'll be quizzed on this stuff too. You won't be quizzed on the properties. I'm not quizzing you on that'll be on a test later on, but the quiz is being able to locate these things. So in other words, the quiz is practicing location. With a periodic table, if I give you nickel, you tell me what, group of things does it fall in. It's a transition metal, right? So it's a location type scenario, all right? And I'm not going to leave that up. I'm going to move on. Oh, what did I just bring on? Transuranic? Is that what was missing? Oh, no, the arrow. Okay, that's silly. All right. And, oh, that's transuranic as well, all the way across the bottom. Okay, so now 2 or 3 more slides, and then I'll be finished. And the extra time that you have here today, you can work on the MSDS thing, all right, and get that finished. But what I want to do now is I want to go back and I want to talk a little historically about the periodic table. What we just talked about here is the way it looks right now. But how did this table of elements come about? Well, I was telling you a little story at the beginning about Lavoisier, and how Lavoisier was very important in chemistry because he kind of systematically named everything. It's interesting. Antoine Lavoisier, before I get to Mendeleev, was a very strange guy. He was super organized, and he lived in France during the French Revolution, and his family had money. And so he was able to do science because his family had money. But that makes him an aristocrat as well, and they weren't very liked during the French Revolution. I don't know a lot of history, but when history collides with science, I learn a little bit about it. And he was very meticulous at writing things down. He kind of perfected the chemistry experiment because he was one of the first to use scales to measure everything he was doing. So he would measure masses before and masses at the end. He came up with the law of conservation of mass during an experiment. And he was very good at organizing and getting things in a way that, was understandable, hence the elements. He was also good at organizing things like tax collection. And he and his family were very good at collecting taxes for the king, but unfortunately was disliked for that particular situation. So when the revolution took place, he was one of the first to lose his head, went into guillotine, and he was about, I think he was late 30s. It was actually quite a blow to chemistry because he was doing such good work that, killing this guy, we stopped the progression that he was doing. But he was such a strange guy. He at one point did an experiment where he lived off of drinking milk only for something like 6 months. Just milk. He would, sip it out of a bowl like he was eating soup, and that's it. So he could see the physiological results. I recently read, and I mean recently, I got a book for Christmas on history of science stuff, and I like this type of stuff. It's kind of neat. I recently read that there's a myth, a rumor, I don't even know what you'd call it, that when he was sentenced to death, he asked his assistant to watch carefully once his head was severed from his body to see how many times his eyes blinked before they stopped. But that's wild. I read that, I'm like, are you kidding me? This guy is like science to the end. Are you kidding me? What, he's going to consciously try to blink as many times as he can as he loses his head? That's good stuff. That's like what stuff? Anyway, so it was this kind of fastidiousness to being very watching and observing, which kind of led him to get chemistry in order for people to do chemistry. That's kind of neat. Of course, he lost his head in the process. So what did Mendeleev do? Mendeleev was actually a college teacher, or a college professor, you might say. And he found that his students had difficulty learning the elements because they were just a list. And it was a list and then some properties and just memorize. And he felt there had to be a better way to do this. He was actually also a card player. He liked playing cards. So what he decided to do was to take some cards, like cue cards, and write down the name of the element, its mass, its properties on these cards. So then he was fiddling with these cards and he decided there's got to be a way to organize this information. So he decided to lay the cards down in order from lightest to heaviest. So he started to lay the cards down, and he found that as he got so far down the list, he would see a card where the properties of that element were very similar to the card at the beginning of the row. Now, not including hydrogen, so let's not worry about that because it's a special case. So he would start with lithium, and he would lay the cards down in order of their mass. And when he got to fluorine, these noble gases hadn't been discovered. His next card would have been sodium, and instead of putting it there, he said, wait a minute, sodium is chemically very similar to lithium. I'm just going to start a new row. New row. Work his way across. Oh, potassium is very similar to sodium. New row. Now you might think, that's not a great discovery. What's so great about, observing that there's a similar property and starting in a new row? What really kind of vaulted this periodic table into the most important chemical discovery, of all history, is that he was working his way along, and some of these elements hadn't been discovered. At the time of this, there might have been 60 elements, maybe less, maybe about 60. And he was working his way along, and he got to the space where gallium should have gone. But gallium hadn't been discovered. So germanium was going to be the next card to be put down. But he realized germanium's properties were so much more like silicon than aluminum that he couldn't put it there. So he said, I predict, and that's what makes this powerful, that there's a missing element here. I predict that germanium needs to go into this position, and by looking at the properties of aluminum, zinc, and germanium, he actually predicted what the properties of gallium should be. He predicted an approximate mass halfway in between. He predicted the way it should chemically behave. The very next year, chemists said, all right, well, if we know the properties, we should know where to find it, because certain elements with certain properties tend to aggregate in the soil in certain ways. And in the end, the very next year, they discovered gallium. Now that's important. That's a theory. As soon as he left the blank, he was saying, I believe, I predict that something should go here. Then finding it is empirical evidence to support the theory. So that's what made it really, really powerful. And within the 10 years after this was predicted, or after this table was developed, the number of elements went from 60 to 90 within 10 years. So from all of history up to 1869, 60 elements discovered, and within the next 10 years, 30 more elements discovered, because they knew what they were looking for. All right. So his periodic law states that the elements arranged in order of increasing atomic mass show a periodic recurrence of properties called periodic trends at regular intervals. That's why we call these periods. It means their properties repeat periodically, just like the moon goes around the Earth periodically in a certain amount of time. Okay, so you don't have to write this down. This is, again, a little reproduction of his predicted periodic table. And again, if we work our way along here, I'm trying to find where gallium goes in here, right there, right after zinc. There's some blanks that he left in there. And like I said, soon after, there was discovery of many elements. So what is a periodic trend? Let's define that. A gradual, consistent change in properties such as melting point, boiling point within the periods and groups of a periodic table. Now, our current periodic table is not ordered in order of atomic mass. If I take a look at all these mass numbers, and they're on my table here, it's these big dark numbers along the bottom. When I get to right here, cobalt 58.93, and then nickel, the next one 58.69. So nickel is lighter than cobalt. On Mendelev's periodic table, they would have been inverted. All right? Now, because they're in the transition metals, their properties are really similar. So he wouldn't have realized that there was an inversion there because their properties are really close anyway, right? So what do we got? Cobalt and nickel. Again, they're both magnetic. They're very, very similar. Shiny, you know, all that type of stuff. So what happened that fixed this problem? Well, number one, there was discovery of something called the atomic number. And in the end, this gentleman by the name of Van den Broek said, instead of ordering it by atomic mass, let's do it by atomic number. So what happened between Mendeleev and this guy here, and this is in 1890s, this is about 20 years later, something called the atomic number was discovered. Now, we know the atomic number to be the number of protons in the nucleus, but the atomic number was actually measured experimentally before they even knew about protons. This tube here that I have in front of me is an X-ray tube. It was invented in the late 1800s, 1894, I think. A guy by the name of Wilhelm Röntgen invented this tube. Well, he first accidentally discovered the X-ray, and then he mastered it by creating a tube like this. And this X-ray tube produces X-rays. So what did scientists do when they discovered X-rays? Well, they shot X-rays at everything that they could find, right? They shot X-rays at people. It was actually his wife. The first X-ray is his wife. Hey, honey, come here. Let me plug this machine in. Little did they know that those X-rays could cause cancer if you X-rayed too much. They used X-rays for everything. They even had shoe companies. Come on, we've got a new X-ray machine. You don't need to try on shoes. We'll X-ray your feet to see what size they are, and then we'll just sell you the shoes. And then they realized people were getting cancer from all these X-rays, so they dialed it back a little bit. But what were chemists doing? They were firing X-rays at all the elements. And what did the elements do? They produced their own X-rays, and they were shot out. But the X-rays that they produced were of a different color. They were slightly different than the X-rays that came in. When the chemists did the mass of the X-rays that they were looking at that came out, and they did some, weird calculations, they had to take a square root, they would get a number that was very regular. For hydrogen, when they did the math, equals 1. They didn't know helium. No, they didn't have helium at the time. Well, they might have just discovered it. Lithium, 3. Beryllium, 4. They didn't know what was happening. They didn't know why they were getting this mathematical thing, but they were getting a number. So they called it the atomic number. And then Van den Broek said, well, you know what? This is a very special number for elements. We don't know what it is yet. But why don't we put the table in order of that? And when they did, they had the current table that we have now. It turns out that this number and these X-rays come from electrons jumping around in their orbits and producing them. And depending how many protons are in the nucleus, as they do their thing, they give off a special type of X-ray, and that's where the atomic number came from. All right. So that's the end of my lesson here on the periodic table. You've got a couple of problems there to work on in terms of just practice. You've also got the MSDS sheet thing that you can complete as well. I think it's due tonight, right? Okay. So I'm going to stop the recording at this point. And boy, I really hope the audio works because I got to go to a hockey game, and if it didn't, it's going to be catastrophic.